Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 3 on power functions and polynomials. We're now going to move into a set of lessons where we explore polynomial functions, right? For the last few lessons we've been just kind of reviewing polynomial terminology and how to factor polynomial expressions. But now we're going to really get into polynomial functions, f of x equals, right? And we want to understand why their graphs look the way they do, why they have the x-intercepts that they do, and things like that. And we're going to tie them into a very simple type of function that we saw earlier in this course called a power function. So let's start by reviewing a little bit about power functions. Power function review. Before we start to analyze polynomials of degree higher than 2, which were quadratics, right? We need to revisit power functions, which we first saw in the last unit. Their formal definition is reviewed below. Let's take a look. Power functions. A power function is one that has the form f of x equals a times x raised to the b, where a and b are real numbers not equal to 0. Awesome. Okay, so power functions are basically one of the simplest type of functions out there. They're monomials, a single term, no pluses or minuses in them, and they're just a number times x raised to an exponent. So let's take a look at a very simple exercise concerning power functions. Exercise number 1. For each of the following power functions, state the value of a and b by writing the equation in the form y equals a times x to the b. All right, this is pretty simple, and it is a skill that's very, very important, especially in both pre-calculus and calculus, two courses I hope all of you are planning to take. Let's take a look at letter A. Y equals 3 divided by x squared. Great. Well, if I want to write this in power function form, y equals a times x raised to the b, then the first thing I might want to do is rewrite it as y equals, no dot there, 3 times 1 over x squared. I could then take that and rewrite it as 3 times x to the minus 2. So there I have it written in power function form where a, the coefficient, is 3, and where b, the exponent, is equal to negative 2. All right, that's it. What I'd like you to do is pause the video right now and see if you can do the same thing for letters B, C, and D. All right, these are all pretty similar and fairly simple manipulations, but you never know, right? So in letter B, we have 1 divided by 7 times x cubed. I could rewrite this as 1/7 times 1 over x cubed. And then I could write that as 1/7 times x to the minus 3. That would be its power function form, where the coefficient is equal to 1/7 and where the exponent is equal to negative 3. All right, so simple enough. Now in both A and B, the exponents are integers. Granted, they're negative integers, but they're integers, okay? In letter C, we've got y equals 8 times the square root of x. Boy, that doesn't look like a y. Y equals 8 times the square root of x, which I could rewrite as 8 times x to the 1/2, and there it's in its power form, right? The coefficient is equal to 8, and the power is equal to 1/2. If these are seeming awfully simple to you, great. Again, I want them to be relatively easy. Now the last one's probably the trickiest of them all, but still not too bad. Let's take a look at it. In letter D, we have y equals 6 divided by the cubed root of x. We can rewrite this as y equals 6 times 1 over x to the 1/3, right? Which means that we can write this as y equals 6 times x to the negative 1/3. There's our power function form, where our coefficient is 6 and where our exponent is negative 1/3. All right, let me circle all those coefficients and exponents just so that you have more things in boxes. Okay, all right, so very, very simple. We just wanted to review what power functions were. You're probably wondering, why didn't I have anything written like y equals negative 2 times x to the 7th? Well, those are such simple power functions that they're already written in power function form, so there would have literally been no manipulation whatsoever on those. Anyhow, now let's get into the heart of it. Power functions with whole number exponents. In this lesson, we will concentrate on power functions that have positive integer powers. In other words, whole number powers. X to the second, x to the third, x to the fourth, x to the fifth. So no x to the 1/2, no x to the negative third, none of that. And the reason that we're going to concentrate on power functions that have simply whole number powers is because those are the same types of powers that polynomials have. So let's take a look at some very, very simple power functions in exercise number 2. Using your calculator, fill in the following values for common power functions. Y equals x squared, y equals x cubed, y equals x to the fourth, and y equals x to the fifth. Now, you may not need to use your calculator to do these, right? So for instance, let's fill in the row for y equals x squared together, right? We're just taking our inputs of -3, -2, -1, 0, 1, 2, and 3, and we're squaring them. So when I square -3, I get 9. When I square -2, I get 4. When I square -1, I get 1. When I square 0, I get 0, 1, 4, and 9. Right? Real simple. Now, you might think, well, now that I'm going to cubing, right, that's going to be a little bit harder because now I have to cube -3, cube -2, cube -1. But you can actually fill in this table pretty easily with or without your calculator by kind of going down a column now instead of across a row. Why? Because x cubed is just x squared times x. So if I want -3 cubed, I could take -3 squared and multiply it by -3. That means that -3 cubed would be -27. And if I wanted -3 to the fourth, that would be -3 cubed times -3, which would be positive 81. Then for x to the fifth, -3 to the fifth would be 81 times -3, which would be negative 243. All right, what I'd like you to do is finish filling in this particular table. Pause the video now, whether you use your calculator or not, and I would encourage you to just go it without the calculator, fill in the table, and then we'll talk about it a bit. All right, well, I'm going to actually fill in down, and it's pretty easy, right? So here I've got -2 squared is 4, -2 cubed would be -8, -2 to the fourth would be positive 16, and -2 to the fifth would be -32. 1's pretty easy. 1 cubed, -1 cubed is -1, then -1 to the fourth is 1, -1 to the fifth is -1, 0 is as easy as you get. And now with the positives, it's pretty easy. You know, 1 squared is 1, 1 cubed is 1, 1 to the fifth is 1, 1 raised to any power is actually equal to 1. It's awesome. 2 cubed is 8, 2 to the fourth is 16, 2 to the fifth is 32, 3 cubed is 27, 3 to the fourth is 81, and 3 to the fifth is 243. All right. Now we've got the table. Okay, and you can already notice some things about the table. For instance, for y equals x squared, the table is very symmetric, 9, 4, 1, 0, 1, 4, 9. But for y equals x cubed, we have -27 here and positive 27 there. -8 there, positive 8 there, -1, positive 1, etc. One thing that's important for you to get good at is just the idea that if I've got a power function with an odd power, right, and these are just simple power functions, that is, then when I take a negative and I raise it to an odd power, I get a negative result. And when I take a negative and raise it to an even power, I get a positive result, right? So -2 to an even power, positive result. -2 to an odd power, negative result. Same thing with -1. Of course, when I have positive numbers and I raise them to any real number power, I always get a positive result, regardless. Now, what I'd like to do is I'd also like to look at the graphs of all of these simple power functions. So, exercise number 3. Using your calculator, sketch the power function below using the indicated window. All right, now what I've done is I've kept the window the same each time. So in each case, I'm going from -5 to 5 along the x-axis and -10 to 10 along the y-axis. So let's go in and let's just set up our calculator to sketch y equals x squared over this particular window. I've already got my graphing, program ready, so I've got x squared. All right, I'm going to hit enter. All I want to do is just change my window to be what I want, so I should go into window, -5 to 5. Come on. Negative 10 to 10. And there's my parabola, right? We knew that that was going to be a parabola. We should have been able to kind of sketch that all on its own. But I get something like that. Also notice, right, that symmetry, right? If I go to negative or positive, I'm getting the same y value out, right? Y equals x squared is an example of an even function. Remember, even and odd functions, those are actually named the way they are based on these exponents. All right, let's take a look at y equals x cubed. The great thing here is I can just go in here, I can go into my graph entry edit, hit the up button, and go in and just simply change my exponent to a 3. And since I've already set my window, I don't have to change anything, right? Here I've got y equals x cubed. And notice again, instead of getting a parabola, I get negative y values here and positive y values there. So I get something that looks a little bit like this. And again, we don't need to make this look exactly perfect. I just want to get it relatively correct. Pause the video now, and why don't you go ahead and get sketches of y equals x to the 4th and y equals x to the 5th. Take a moment to do that. All right, let's quickly take a look at them. Again, I'm just going to go into Menu, Graph Edit, Function, go up, whoops, change that to a 4th. And now notice, we get something that doesn't look all that different from y equals x squared, except, if you will, it's a little bit flatter on the bottom, all right? If that's a great term for it, I don't know. It's flatter on the bottom, but it still has got that beautiful even function symmetry, right? Something like that. And likewise, if I, oops, nope. If I go in and I change now my x, whoops, no, I don't want to go that direction. That'll take me forever. Come on, there we go. If I take a look at x to the 5th, I see a very similar thing, right? X to the 5th ends up being a graph that looks a lot like y equals x cubed, but it's a little bit flatter around the origin. I don't need to worry about that so much as the fact that it looks a lot like y equals x cubed, but it definitely grows faster. Now notice, of course, that these 4 graphs look very similar if you compare y equals x squared and y equals x to the 4th, y equals x cubed compared to y equals x to the 5th. What we now want to do is just get down some general trends, okay, based on both the table and on the graphs. So let's take a look at exercise number 4. Based on the last 2 exercises, fill in the following sentences. Letter A. If b is odd, the power function y equals a times x to the b will have blank outputs for opposite inputs. All right, so if the power is odd, then what will be true about the outputs for opposite inputs? Pause the video there. And if b is even, the power function axb will have blank outputs for opposite inputs. Pause the video and see if you can fill those in. All right, well, this is truly the definition of odd and even functions, right? If the exponent is odd, then that power function will have opposite outputs for opposite inputs, and if the power is even, it will have equal outputs for opposite inputs. So y equals x squared and y equals x to the 4th don't care if the input is negative or positive. It's going to give you the same thing, right? And that's why we get this great symmetry. I can literally draw a horizontal line on, and those 2 outputs are the same for those opposite inputs. Same thing for y equals x to the 4th. On the other hand, if I went here, right, I would find that those opposite inputs gave me opposite y values, opposite outputs. You can definitely see that in the table, and we kind of pointed that out, right? For y equals x cubed, I have negative 8 here, I have positive 8 here, but for y equals x to the 4th, I have positive 16 here and positive 16 there. So, important trends. Now let's take a look at exercise number 5. Based on the table and graphs, fill in the following. Letter A, if b is odd, the power function y equals ax to the b will have ends that point in blank directions. And if b is even, the power function y equals a times x to the b will have ends that point in blank direction. All right, see if you can fill those in to make the sentences make sense based on what you saw. Well, this is really all about the graphs, right? You can't see it so much from the table, but if I look at those graphs, right, if I've got odd-powered functions, then the ends are going to point in opposite directions. That end is pointing up, that end is pointing down, that end is pointing up, that end is pointing down. But if I've got even-powered functions, right, that don't care about whether the input is negative or positive, then the ends point in the same direction, both pointing up here, both pointing up there. So, if b is odd, the power function y equals ax to the b will have ends that point in opposite directions. And if b is even, the power function y equals ax to the b will have ends that point in the same direction. All right, and that's actually very important. It means that power functions, right, that are odd will always cross the x-axis at some point. Power functions that are even, right, well, those will intersect the x-axis right at the origin, and then they'll either go up or they'll go down. So let's take a look at our next problem. Exercise number 6. Which of the following power functions is shown in the graph below? Explain your choice. Do without the use of your calculator. All right, we'll pause the video now, right? Look at this thing. And even though it doesn't look exactly like one of the 4 graphs that we graphed, you should be able to figure out which one of these 4 choices it is based on what we just talked about, and also based on transformation work that we did a few units ago. All right, well, the fact that both ends point in the same direction means that the exponent must be even. So let's just kind of write this down. Both ends point in same direction. That means power is even. All right, and that means it can't be choice 1 and it can't be choice 4. Now, choice 2 is y equals negative 3x to the 10th. And choice 3 is y equals positive 6x to the 8th, okay? And notice, right, in our previous slide, when the coefficient on all of the power terms was a positive 1, the ends of the even functions pointed upwards, okay? The only way to flip them and have them point downwards is if their coefficient is negative, right? A negative coefficient is going to flip a graph over the x-axis and have it point down if it is an even-powered function. So the choice has to be choice 2, because both ends point down, coefficient must be negative. And of course, you could easily check that by graphing on your calculator, but we wanted to make sure we could do this without the calculator so that we truly understand both how the exponent affects the nature of the graph and how the coefficient affects the nature of the graph. All right, now we're going to do one last exercise here, and this is probably the most important one of what we're doing today, the end behavior of polynomials. The behavior of polynomials as the input gets very large, as it heads towards infinity, or very negative as it heads towards negative infinity, is important to understand. We will explore this in the next exercise. So let's take a look at exercise number 7 and make sure to have that graphing calculator ready. Consider the two functions f of x equals 2x cubed minus 5x squared minus 29x plus 30, and g of x equals 2x cubed. Now let me be very clear before we even get to this, right? F of x is just a stock polynomial, right? G of x is a power function. F of x is not a power function, right? But they obviously share something in common, all right? They share this particular term, right? But they're definitely different, right? Because this one, as well as having the 2x cubed, has minus 5x squared minus 29x plus 30. Now, this particular problem is just a bunch of graph it using this window, then graph it using this window, then graph it using this window. And what we're going to do is we're going to take a look at the functions, the two functions, when the inputs are relatively small. X is negative 10 to x is positive 10. Then we're going to allow the inputs to get bigger and even bigger still. All right, and we're just going to keep doing that and seeing and comparing the two graphs. So let's begin and get these two into our graphing calculator. Then all we're going to be doing is changing the window. So let's do it. Let's bring out our graphing calculator. All right, bring this thing over. Let me get the two in. I'm going to go menu. Let's see, graph entry edit, function. Oh, no. Sometimes this particular emulator. Let's go. So we've got 2x to the third. That's not 2x to the third. That is 2x to the third. And great. And now I want 2x to the third minus 5x squared minus 29x plus 30. Okay, don't worry about that. I still want to get the right window. So the menu, window settings. The first window I want to look at, negative 10 to 10. And then my y window is going to be negative 100 to 100. Okay, great. So we've got our two functions, right? The one in blue is our y equals 2x cubed. It's our nice simple power function. The ends point in opposite directions because it's a power function, right? Also, it's, the end is pointing up here and the end is pointing down there because the coefficient 2 is positive. Now our other polynomial, that cubic polynomial, way more complicated, right? It's got these two beautiful turning points, very, very different, okay? We just kind of want to get a sense for it. Now let's change the window again. All right, I'm going to go in. All I'm doing is changing the window, thankfully. Okay, my new window settings are going to be negative 20 to 20 on the x and are going to be negative 1,000 to 1,000 on the y. All right, great. Now, as we look at this, right, remember the red, right, the blue is going to be our power function and the red is our more complex polynomial. Now in our first graph, those two looked very different. In this one, they're starting to look kind of a little more similar, right? Now you can still clearly see a difference. It's not like they're lying on top of each other or anything, right? But they certainly show a lot more similarities in this particular window than they did in the previous one. So let's take a look now at our next window. All right, in this one, we want to go from negative 50 to 50. And notice what I'm doing is I'm really starting to look at more long-run behavior. Here I want to go negative 10,000, so I'm just going to add another 0 on there and another 0 on there. Negative 10,000 to 10,000. Oh my goodness. Now again, imagine that you're just sort of like looking at something and you keep backing away from it. Now, right, you can't even see the turning points anymore of that more complex polynomial. And in fact, it's almost looking like the two are lying on top of each other for all intents and purposes, right? But there is still, I can still see that difference right in here. Definitely still a difference there that I can see. Now let's take a look at one more window. So let's go back into here, window settings. We're going to now go negative 100 and 100. And now I'm just going to add one more 0 on here. So I've got negative 100,000. Whoops, and that is not what I wanted. And positive 100,000. And now right, you can barely see a difference. Those two almost look like they are lying right on top of each other, okay? Right on top of each other. You know, you can barely see anything down here in terms of daylight, maybe like a little bit up here. But you could probably imagine that even if I opened it up a little bit more, so now maybe x was going from negative 1,000 to 1,000, maybe y going from negative 1,000,000 to 1,000,000, right? We wouldn't see any difference between those two whatsoever, okay? So what is the point? Let's kind of get into this. All right, letter E. What do you observe about the nature of the two graphs as the viewing window gets larger? Well, what I notice about the two graphs is that they look more, let's see if I can spell the word and correctly. They look more and more alike. They simply look more and more alike, right? Now, letter F. Why is this occurring, and what does it allow you to conclude about the end behavior of polynomials? All right, now this can be very tricky because, you know, as you grow up and you work through math, you know, you use your graphing calculators or calculators in general more and more, right, to do calculations, as it should be. Nobody wants you multiplying and dividing decimals by the time you get to this level. You want all of that kind of, you know, sort of like manipulations to be done on a calculator. But you can also start to lose some number sense, right? So why is it occurring? It's occurring because when x gets to be very large, and when I say x is very large, I mean both in a positive sense and a negative sense, right? Cubing a number gets to be much, much larger than squaring a number or raising it to the first or that 30 tacked on. So when, right, x gets very large, we say that the 2x cubed dominates the behavior of the polynomial. It is the most important part when x is very large, because when you cube something that's large, it gets really big, right? And it gets much bigger than squaring or raising to the first, okay? So why is this occurring? When, maybe I'll say the absolute value of x gets very large, the 2x cubed in the polynomial dominates all other terms. All right? Now, what does this allow you to conclude about the end behavior of polynomials, right? It tells you that the end behavior of polynomials, right, the end behavior being what happens when x goes to infinity and negative infinity, all right, the end behavior of polynomials only depends on its highest powered term. All right, so let's get that down. This means the end behavior of polynomials only depends on the highest powered term. And that's great because since I can easily say what the end behavior of any power function is, right? Any power function, I should be able to tell what the end behavior is by just looking at its coefficient and whether its power is odd or even. Then, if I want to know what the end behavior is of some very complex polynomial, I don't need to worry about the 5x squared, the negative 29x, and the 30. Now, those three terms make a huge difference in terms of what's known as local behavior, right? Turning points, zeros, and things like that. But if I simply want to know what is this polynomial doing when x heads to infinity or when x heads towards negative infinity, then all I have to do is ask myself, what does 2x cubed do as x heads towards infinity or negative infinity, right? And we can really see that again by just taking a look at this graph, right? We knew that 2x cubed was going to head up towards infinity as x got really big, and was going to head towards x equals negative infinity, or sorry, y equals negative infinity as x got really big in this direction, and that is then exactly what that more complicated polynomial did as well. All right, so let's wrap this up. Now, we saw a lot of things in this lesson. All right, we reviewed what a basic power function was and how to write something in power function form. We then just concentrated on power functions that had whole number exponents and really kind of dug into the difference between a power function that has an even power, where the two ends point in the same direction, and a power function with an odd power, where the two ends point in opposite directions. We also saw how the coefficient of a power function will then determine whether the ends point up or down, or whether they go like this or they go like this, and you'll play around with that a little bit on the homework. And finally, that very important last exercise, where we saw how the behavior of more complex polynomials in the long run all just depend on its highest powered term. All right, and we're going to work a lot more with that in the coming couple lessons. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. I'm Kirk Weiler, and until I see you again, keep thinking and keep solving problems.